Okay, so this is still in Packet 3, Topic 5, differential equations. So for differential equations, this is where we separate and then integrate and then plug things in. We had a couple different words, algebraicate, forget what the other words were, but find C, basically. Separate the variables, integrate both sides, plug in information to find C. Just as a side note, this is also a fairly common type question. Again, look at the years: 2017, 2016, 2015, 2013, 2012, 2011. So pretty common type of problem. Just as a side note, it's also where like some of the famous problems come from. You've never heard of these problems, but within calculus circles, these are some of the famous ones. The boiled potato problem, we're not actually going to do that one. The baby bird problem, we'll do that in a minute. So that's just, these problems take on a life of their own afterwards because students walk out of the testing center complaining about them. The potato, I didn't know how to do the potato. Anyway, the ones that'll be due are these 4, 2, 3, 5, and 6. 2, 3, 5, and 6 is the ones that will be due. And I'll do 2 and 5, and that will leave you for 3 and 6. So let's look at number 2. Consider the differential equation dy dx equals x squared minus 1/2 y. Again, it's usually worthwhile to take a second before you even start reading questions to ponder the statements. Like, what have they given me here? And the answer is not much. I also look at that and then think, wait a minute, I don't think I can separate and integrate that one. So I hope they don't ask me to, because I would be stuck on that one. Well, let's see what they ask for. Find the second derivative in terms of x and y. Okay, I've got a first derivative. They want me to find the second derivative. So what should I do? Yeah, I'll take a derivative of both sides. A d dx derivative, so no t's involved. It's not yet anyway. So second derivative. And then I didn't get to pick on people yesterday, so. Luke, how about the derivative of x squared? 2x. Jameson, how about the derivative of negative 1/2 y? Yes, there we go. Again, the dx means we have to be careful when our derivative is not of x things. Okay, they asked me for the second derivative in terms of x and y. Does this count as an answer? You're shaking your head no, it doesn't. Why doesn't it? What's wrong with it? It's not wrong, it's just... Right, it's not in terms of x and y because there's this dy dx there. But we have dy dx. So in place of dy dx, we'll put that. So the second derivative then is 2x minus 1/2 x squared minus 1/2 y. And who knows, I could distribute the negative 1/2 and that would change some signs and some fractions, but why bother? Why risk messing things up? Maybe I could do it later if I need to, but for now, that's all I need to do. That's the second derivative in terms of x and y. Part B. Let y equals f of x be the particular solution to the given differential equation. Okay, so we don't have that solution, but there is some solution out there where that's the answer to this problem, and whose graph passes through negative 2, 8, Does the graph have a relative min, relative max, or neither at the point -2, 8? Justify your answer. Okay, well, mins and maxes. So that's what a max looks like. There's what a min looks like. So how could I tell if a particular point is a max or a min? Okay? There's two answers to that. That's one of the answers. If the derivative changes signs, like as we move left to right, am I going from increasing to decreasing or decreasing to increasing? That's correct. The trouble is, as I move left to right, I don't know what y is, so I wouldn't be able to plug in a y value. So I could plug something in a little less than -2 and a little more than -2, but since it also depends on y, your statement's correct, but it doesn't help on this problem. There's another way to consider maxes and mins. What else is going on at those spots? I'm trying to give hints there with my pictures. What's the derivative equal to at a max or a min? 0. So let's take a derivative, or let's find the derivative. We already have the derivative. Let's evaluate the derivative at -2, 8. And if that's 0, then there's more work to do. If it's not 0, then we could say neither. I'm guessing it's going to be 0 just because that would kick us into doing more stuff. So x squared minus 1/2 of 8. 4 minus 4 is 0. Well, sure enough. So it's a flat spot on the graph, but I don't know if it's a flat spot at the top of a mountain or the flat spot at the bottom of a valley. Well, what's the difference between these two pictures? Like, the similarity is y prime equals 0. Got that. Concavity. That will be my determining factor on whether that's a max or a min. Which makes sense, because what do you have to know in order to answer concavity? Second derivative. What did problem A ask us for? Second derivative. So they sort of gave you a hint in this problem of, hey, find the second derivative, and then I'm asking this question that just happens to need the second derivative. So the second derivative at -2, 8. Back at my answer here. Although it might be wise, which one of these formulas would be easier to use? First one or the second one? I think it should give me the same thing. Why the first one?
Because we already know what dy dx.
We already know what dy dx is, so I don't need to use this formulation of it because I have an answer for dy dx. The whole answer is 4. -4, yeah. I'm going to use that first one. 2 times -2 minus 1/2 of 0, because we just found that the derivative is 0. So the second derivative is -4, which means we're concave down. And y prime equals 0. Sort of justifying my answer here. So what's the conclusion? If we're concave down and at a flat spot, so there's a horizontal tangent. What exactly is going on at this point, though? Is a max, yes. So -2, 8 is a relative max. Yes, sir.
You put in 0 for and it's a -1/2 times 0 because I'm using.
I used this equation for my second derivative.
So how do you get? I get why you plug in -2, but why do you plug in 0?
Because it called for dy dx, it called for the derivative.
Oh, okay.
If I had used this one, it would have taken a little bit longer. So like at -2, 8, I could plug in -2 minus 1/2 of negative 2 squared minus half of 8. But all of that's 0. So I still get negative 4.
Okay.
And I almost used that one because that was the one I boxed. And that's probably what most people would use. But then I saw that I already knew dy dx. Either one would be fine. This one might take you 5 seconds longer. Maybe not even that much. So relative max. Let's see, did we answer that question? Relative min, relative max. Justify your answer. Yeah, relative max, and I'd say we justified our answer. The fact that it's a flat spot and concave down, that makes it a max. By the way, you can mark out part D. That involves a Calc BC thing. Sometimes when they put the same problem on both tests, they won't put all the parts to it. There's a Calc BC part. So part D we can mark out because we don't use Euler's method. All right, part C. Let g of x be the particular solution to the given differential equation with g of negative 1 equals 2. Find the limit as x approaches negative 1 of g of x minus 2 over 3 times x plus 1 squared. Show the work that leads to your answer. Okay, what's first go on finding limits? Always the first attempt. Just plug it in. It's a substitution. Hope that you get an answer that works. Pretty sure we're not, because like this is part C of a AP test question, so it seems highly unlikely that just plugging in negative 1 is going to work. But that's what we start with and see what happens. So in goes negative 1. And g of negative 1, they told us is 2. 0 over 0. And we're taking limits, and we get 0 over 0. L'Hopital's rule. So now I realize, this is a L'Hopital question. So L'Hopital's rule, what do you do for L'Hopital's rule? Derivative of the top, derivative of the bottom, and you don't have to worry about quotient rule. You just take the derivative of the top and the bottom. You know what? I'm going to go back and say it doesn't equal those because it's not 0 over 0. So let's use L'Hopital's rule. All right, I guess I know what g of x is, so I'll just put g prime of x. Derivative of negative 2 goes away. And in the bottom, 6 times x plus 1 to the first. Times 1, if we want to make sure we emphasize the chain rule there. Alright, well I need g prime at negative 1. Right. Again, after you do L'Hopital's rule, it's substitute again and see what happens. Although, I've got 0 in the bottom, so I'm suspicious that this is, I don't know what's happening, but this is not going to be a final answer, whatever is going on here. Alright, well, how do I find g prime? I don't have an equation for g. But at the very beginning, I've got dy dx. So I need to come out to the side and do dy dx at negative 1 comma 2, because that's the point I'm dealing with here. So negative 1 squared minus half of 2. 1 minus 1 is 0. I get 0 over 0. So I get to use L'Hopital's again. Limit x approaches negative 1. the second derivative. But now I'm kind of onto their ways. I'm like, okay, we found the second derivative, so I'll be able to plug something in there. Derivative of the bottom, yeah, just 6. You could distribute the 6 and then take the derivative, maybe. Okay, so this is going to be it, because I'm definitely not getting 0 over 0. I'm getting something over 6. So the second derivative at -1, 2. Go back and find the second derivative equation somewhere I can use. Oh, it's that same issue of I could use the first formulation or the second formulation. Again, dy dx is 0, so it might be easier to use that first one. 2x minus half of dy dx. Right, because dy dx was 0. We got that on that last one. So 2 times -1 is -2. So the second derivative is -2 over 6. Reduce it if you like, but also kind of done. And maybe we should make the final statement to be clear. So as x approaches -1 of this limit, that equals -1/3. L'Hopital's twice. And take a peek at the timer. We're coming up on 17 minutes, so that's not bad. It's supposed to take 15. I did a little bit of intro commentary, and then we explained things as we went, so we're on track time-wise. Questions on that one? All right, that one's... Keep using L'Hopital's rule. Now, if you run into some situation where you use L'Hopital's rule 5 times and you're still at 0 over 0, then you probably did something wrong. Because you would also run out of derivatives, right? We didn't find a third derivative. But yes, the answer is if you get 0 over 0, keep doing L'Hopital's. And hope that they don't have you do it more than twice. All right, we're going to skip ahead to 5, but peek at 3, and it's pretty similar. It gives you a dy dx with an x and a y in it. So part A is just sketch the slope field, plug in points. Part B, find a second derivative in terms of x and y, so that mirrors pretty closely what was going on. It asks a question about concavity, but concavity goes with second derivative. And then it asks that same question. Min, max, or neither at x equals 2. And then part D, it's a little bit different. So again, you work enough of these free response questions, you start to see they kind of repeat, and toward the end, they like to mix it up on you. Okay, so you're assigned number 3. We'll skip number 4. Although you look at it and it's another one where they give you dy dx with x's and y's. Find that limit. I would bet almost anything this is another L'Hopital problem. Sine of 0, 0. You're definitely getting 0 in the bottom. Yep. Anyway, you're not assigned 4, but that's L'Hopital coming up. Let's skip to number 5. So I'll do 5. And you'll be assigned 6. Yeah. The baby bird problem. Another one that students walked out of the room complaining about. And then the next day they released it, and all the calculus teachers were like, "Oh, it's not as bad as you guys said it was." The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. Which, I don't know, that sounds tricky, but then they give you the equation, so it's not as bad as it could have been. At time 0, when the bird is first weighed, its weight is 20 grams. Well, that sounds like an ordered pair. So when it's first born times 0, weight is 20. If B is the weight of the bird in grams at t days after its weight, then here's the derivative, dB dt 1/5 100 minus B. Let y equals B of t be the solution to the differential equation with the initial condition, and we already figured that out, B of 0 equals 20. Again, test-taking strategy, don't jump right into the question, make sure you understand the setup information. So, somebody put in words, in fact, Caden put in words, what does dB dt tell me? What is that?
The rate at which he gains weight over time.
Perfect, that's the rate at which he gains weight over time. Okay, so what's it going to ask? Part A, is the bird gaining weight? Oh, so now I know what to use because Caden just told me dB dt is how is it gaining weight. Is the bird gaining weight faster when it weighs 40 or when it weighs 70? Explain your reasoning. So, Holly, what do you think? What should we do to answer this question? What does dB dt tell me? Okay, so how do I figure out how fast it's gaining weight when it weighs 40? Plug it in. So I'll take dB dt when B equals 40. So 1/5, 100 minus 40. That's a safe stop, but I also know I have to compare what it is at 40 with what it is at 70. So I don't know if a safe stop is good enough for me to be able to compare. So it's probably worth it to do a little bit of work here. 1/5 of 60, which is 12. dB dt when B equals 70. So 1/5 of 100 minus 70 is 1/5 of 30, which is 6. Okay, so Kelsey, what's the conclusion?
Whenever he weighs 40 grams.
Okay, so at weight equals 40 grams, he's gaining weight faster. And I'm no bird scientist, but I feel like that makes sense. The younger kids and animals gain weight faster, and as you approach your full weight, hopefully you stop gaining weight, right? Part B. Oh, another second derivative. Find the second derivative. Well, if we've got a first derivative, then we'll take a second derivative. So take a derivative of both sides. I think this one's easier. Whoops. I put 100 in there. That should be 100 minus B. I'm going to distribute that because I think that would be easier to deal with. So that's 20 minus B over 5. I think that's going to be easier to deal with because what's the derivative of 20? 0. So minus 1/5 dB dt. Except I bet it asks for it in terms of t, maybe? Oh, no, I asked for the second derivative in terms of b. Oh, that's not b, though. That's dB dt. So I need to figure out... Morning, Jake. So let's put that in for dB dt. So this is pretty similar to what we did that last time. We took a derivative, but the second derivative has the first derivative in it, so I've got to replace the first derivative with some expression of the first derivative. And again, it's like that could be simplified. Maybe it should be simplified, but that's all I need to say for now. Use the second derivative to explain why the graph of B cannot resemble the following graph. Okay, well, what does the second derivative tell me about a function? Concavity. So I'm guessing there's a concavity issue going on here, which means I think I want to figure out what this thing looks like, or get a better expression here. So that would be -4 plus b over 25. All right. Let's see. So concavity is this thing. Let's see where that's 0. Maybe that will help. So 4 equals b over 25. So when b is 100, that's when the concavity is 0. So let's check out the concavity between 0 and 100. If I plug in b equals 50, I get a second derivative of, what will the sign of my second derivative be if I plug in 50? Negative. So it's that derivative is always, or the second derivative is always negative between 0 and 100. After that it goes positive, but it told us somewhere that its full weight is 100. Its max weight is 100. So this means it should be concave down when b is less than 100. And I think I just answered the question, because that thing's not concave down. That graph is not concave down all the way. It's concave up until somewhere in there. So concave down when b is less than 100, but the graph is concave up when b is between 0 and, can you put a squiggle under an, like meaning up? B is concave up for some b's, for some b, yeah, I don't know what it is, but the graph is concave up. That formula said it couldn't be concave up, so that graph won't work. And maybe you see why students were complaining about this problem. Part C, use separation of variables. Okay, so we finally get to do like the actual sort of differential equation problem here. 2, 3, 5, and 6 for this one. Jake.
2, 3, 5, and 6.
2, 3, 5, and 6. Let's see, separation of variables. Nice that it tells me what to use, so I'm pretty sure I need to separate the variables. So dB over 100 minus b equals 1/5 dt. It's been a while since we've done one of these. Do you know how we're going to integrate the left-hand side? Right-hand side won't be hard. The left-hand side, we can use substitution. Not quotient rule. If you want to use substitution, what do you think u should be? The bottom. So du is negative dB, which I guess that makes sense because that minus sign. So I'm going to put a negative inside and a negative outside. And now I've got du over u. What's the antiderivative of du over u? Natural log. So negative natural log of u. I'm going to go ahead and put in 100 minus b. And the other side is 1/5 t plus c. Okay, so I separated, I integrated. Now I need to plug in 0, 20, but I don't think I want to solve for that yet. Or I don't think I want to do that yet. I want to solve for b. Get b equals something. So I'm going to move the negative sign over. So negative 1/5 t. Remember, if we don't know c yet, then we can kind of play games with it, and c times negative 1 is still just c because I haven't defined what c is yet. All right, what's the next algebra trick to get b by itself? The fishhook thing. So e to the negative 1/5 t plus c equals 100 minus b. All kinds of algebra tricks going on. What about that e to the negative 1/5 t plus c? What's the trick we can do with that? C can come down front. So c, e to the negative 1/5 t equals 100 minus b. So b equals, move things around, 100 minus c e to the negative 1/5 t. And they told me that b of 0 is 20. That's right, because when the bird was born, it weighed 20. So some of you might know already what c should be. Other people might take the time to plug things in. E to the 0 is 1, so c is 80. So 100 minus 80 e to the negative 1/5 t. Separate, integrate, solve for c. Read the question and make sure I answered everything here. The separation of variables defines y equals b of t. Got that? Yeah. The baby bird problem. That we started at time 19 and now it's 33, so that took us 14 minutes. Again, they do a nice job of timing these things out to be 15 minutes. All right, so your job is numbers 3 and 6. Another second derivative there. This packet is due the Thursday of next week. And we'll do the last bit of it, or the last part of it together tomorrow. So if you're really keeping up, you could turn it in Friday morning and be done with it. Up to you.
Which ones are we doing on review topic 4?
FRQ 4, I think we just did 1 through 4.
Oh, we never recorded them.
Yeah. I recorded 1 and 3, I think, and assigned 2 and 4. And then today we recorded 2 and 5 and assigned 3 and 6.